Good evening and welcome to N Simplex Pachinko. This is Obi-Wan Pez. We are going to be doing a bit of math tonight. This is a fairly stormy night, so we'll see how long this lasts. Yeah, good times. I believe most, if not all, of the thunder has actually passed, and hopefully the storm cells that kept me in the basement will be not coming back, or not having more waves. We'll see how it goes. Hope everyone's had a good week so far. If anyone has any questions, as always, drop them in the chat and we'll get there. For right now, we're going to take a look at problem G5. Not helpful. From the Mathematic Educator for this month, proposed by Michael Ecker. We have k plus 1 raised to the k plus 1 is greater than, oops, nope, k to the k multiplied by 2 plus the natural log of k. Alright, for all k in the reals, such that k is greater than 1 over e. Right, so the goal here is to set up a proof. And I've been on a few random spurs of this, and it's come out, yeah, I mean, I haven't finished it, but so my first inclination was to take the natural log of both sides. This ended up with some nasty, messy stuff. Most importantly, right, because this is multiplication, the natural log is going to have two separate terms with addition between them, so yeah, this made a lot of weird stuff going on. So overall, probably not the best. My next inclination was to bring all the tower terms together. So we end up with a k plus 1 raised to the k plus 1 divided by k to the k. It's going to be greater than 2 plus natural log of k. Alright, and then here, what I did was I said, okay, take k of the k plus 1s and put them together. So k plus 1 to the k multiplied by k plus 1. And then on the bottom, you've got your k to the k. It's going to be greater than 2 plus natural log of k. This then can end up with parentheses k plus 1 over k raised to the k multiplied by k plus 1. It's going to be greater than 2 plus natural log of k. And then here we've got something rather interesting. So if we separate these and make it 1 plus 1 over k raised to the k times k plus 1 raised to 2 plus natural log of k. Alright, this term here will always be less than e while k is finite. That might have actually just cracked it. I never actually wrote it like that before. I noticed that we had the definition for e here. So 1 plus 1 over k to the k if you let the limit. Okay, so if we take this thing and we say take the limit as k goes to infinity of 1 plus 1 over k to the k, this is equal to e. Alright, so if this is equal to e, then let me get my colors back here. Okay, then this stuff here is always going to be less than e. And you could check that, just plug in 1, plug in 2, whatever you feel like. And all those numbers are going to be less than 2.7. Alright, so typically I demonstrate this in our compound interest section. So if you compound once during the year, just at the end of the year, you only take interest once. And so that's one period at this 100% rate up here. And then if you take it as k is 2, it's going to be compounded twice in the year. K is 4 makes it quarterly, k is 12 makes it monthly, k is 365 makes it daily, and every time that we do this we're taking a shorter and shorter period, and so it's taking compound interest more and more frequently. So therefore we're getting more money out of the deal. So this means that as k goes off to infinity, we're doing this as many times as possible until it is literally just a continuous increase due to interest. So we always have something that is less than e, which means that this is going to be this thing that we have here. Ugh. There we go. Okay, 1 plus 1 over k raised to the k times k plus 1 is going to be greater than did I just... No, that's right. Okay. Is less than, right, e to the k times k plus 1. That's not going to work, though, is it? Right, because I need something that's between these two. Damn. Oh, well. Wait, no. No. I need something that's between, otherwise it's not going to work. Worth a shot, anyway. So then this becomes an interesting question. What do we do from here to make this work? Alright, so one thing that I did was I divided off the k plus 1 to the other side. So we made this 1 plus 1 over k to the k. It's going to be greater than 2 plus natural log of k over k plus 1. And like from here, I feel like I've done this in Calc 2 in terms of doing a like sequence. So we should still be able to do this in much the same way with a continuous function, where we're looking at this in terms of some sort of like test to say that this thing is always going to be between these two functions, and then sort of like by induction, essentially, say that like all values are always going to end up being less than, or all values are always going to be between these two, and in doing so we can prove that the exponential is always going to be greater than this rational. Alternatively, we can show so graphically we can show where their solutions are. But I feel like that's cheating a little bit. Only a little. It's probably fine. Okay, so no solution. Or if there is a solution, it's far less a quarter. So it's going to be a very, very small number, if there even is one, which it looks like there is not. Yeah, because this is continuous. Okay. Not sure how to show that there isn't a solution, but I get the feeling it's not going to be easy. Next silly question. How much actually is 1 over E? 0.36787. So 0.3. Okay. Alright, stupid idea. So 1 plus 1 over k raised to the k is always greater than 1. Because again, if we're talking compound interest, you're always getting more than the $1 principal that you put in, no matter what. Which is always going to be greater than or equal to this thing. Now we just have to prove it. So easy, right? Alright, 1 is greater than or equal to 2 plus natural log of k over k plus 1. Now we can multiply by k plus 1 because this is always going to be a positive value. Since k is greater than 1 over e. This is going to be like 1.36 or something like that, so that multiplies over at minimum. So we get a k plus 1, greater than or equal to 2 plus natural log of k. Let's get rid of the natural log. This is going to be an interesting thing because it's going to be an exponential. K minus 1 is greater than or equal to natural log of k. Ah. Go the other way. 1 plus natural log of k. This is the natural log of e plus the natural log of k would be less than or equal to k. This may not actually do anything, but nonetheless. Actually, this will do something. Yeah. This could work. I think we may have to actually take up the whole k plus 1 bit, but we'll effectively do. So this is the same as k plus 1 times the natural log of e greater than or equal to 2 plus... Damn. Minus 1. Minus 1. Greater than or equal to the natural log of k. This can then go up as an exponent. This is the natural log of e to the k minus 1. It's going to be greater than or equal to the natural log of k. Yeah, I just did the exact same. Never mind. Alright, since this is 1 to 1, you can also just logs. Get rid of the natural logs because it's a 1 to 1 function. It's e to the k. This one is greater than or equal to k itself. Yeah, okay. Alright, so again, without resorting to natural logs or reversing ourselves back into that little rut there, I'm going to make this work. Mm-hmm. I did this before. I did this on the other problem we were talking about. I want to know when this function has a slope of 1. If that function has a slope of 1, and it is to the left of this particular x value, whatever it is, whatever x value we find for it, then that means yes. So if we say, okay, where is the slope of this function, e to the k minus 1, going to be equal to 1? If it's on the left of this, that means that this is going to pull away faster and eventually go off to infinity. Meanwhile, it will not intersect this. If, on the other hand, we reach a slope of 1 after the line itself, then, yeah, okay. This is probably something very well known. Let's see. And this has to be a thing, right? I can't have just invented something. This is stupidly simple. Or like Newton, I should just take credit for it. That's fine. Probably was Newton in the first place. He could deserve to take down, be taken down a few pegs. It's fine. So the derivative of each of these things, then, the derivative of the function on the left is just going to be e to the k minus 1 times the derivative of the top, which is just going to be 1, needs to be greater than or equal to 1 itself. I don't think I want that. Hang on. Alright, so where does the derivative of this function have a slope of 1? And that value here, you take the natural log of both sides, it's 0 over here, so that's going to be k equals 1. Okay, makes sense. So k equals 1. Right, so they will be tangent only at that one point where the slope itself is going to be equal to the original function. Both are equal to 1. this is e to the 1 minus 1 is greater than or equal to 1. Shows us this is e to the 0, so this is 1. Alright. So y equals x looks like this. They intersect here at this particular point. Point 1, 1. So we want to know when the e to the k minus 1 is going to be greater than or equal to k. It is all real numbers. So e to the k minus 1 is greater than or equal to k for all k in the reals. So since we have that, this says that the natural log of e to the k minus 1 is going to be greater than or equal to natural log of k for all k within the domain. Terrible notation, but I'll deal with it. So basically it's just greater than 0 at this point. Interesting. Okay. So if that comes down, this is going to be k minus 1 greater than or equal to natural log of k. Add 2 to both sides, you get k plus 1. Plus 2. Let me just keep backtracking this. Wow. Well then. I don't know if I'm missing something here. finite compound interest formula, which is then going to be strictly greater than 1 is greater than or equal to natural log of k plus 2 all over k plus 1, and then therefore one plus 1 over k raised to the k is going to be greater than 2 plus natural log of k over k plus 1 for all k greater than 0. Works for me. Oh man. It's a little weird, but it'll work. Alright, if there's anybody around, let me know. I'm happy to pick up problem. You are, of course, free to continue lurking, those of you who are here, and anybody who's here for video on demand, I thank you very much for coming. And in the future, if you want to hang around, you can send me any problems you might have. Alright, let's go back. Mathematical thinking. Probably should have downloaded the resource here before stream started. But that's alright, we were hiding in the basement, so... Eh. Spot up here somewhere. Or not. Sheesh. Thought for sure it just jumped to 100. That's rude. Alright. Actually, we do need to look at this a little bit. Just real quick. Figure out approximately where we left off here. 113, 114. 127, graph of a function is a subset. Yeah. Also, did we get all the... Yeah, we did. A cross B consisting. Gotta love whiteboard. Alright, consisting of the ordered pairs x, comma f at x, defined where x is belonging to A, the domain of this particular function, f. Alright, 128, 129 define graphs of functions. I'm not even going to bother. $130. Alright, example for the function f defined real to real defined by f of x is equal to x over 1 plus x squared. The image is the interval, which goes from -1/2 to 1/2. So if we want to prove that that's the image, we have to show first that absolute value of f of x is going to be less than or equal to 1/2 for all x in reals. This is going to be equivalent to saying that the absolute value of x is going to be less than or equal to the inverse function. No, it's not inverse. What is it? This stuff inside here. So absolute value x over 1 plus x squared less than or equal to 1/2, because here this is always going to be positive. It can be shifted out. This is the absolute value of x. Multiply by 1 over 1 plus x squared. What the hell? Oh, that's 1 plus. I was going to say something's not right there. Perfect. Alright, must be less than or equal to 1/2, and we can multiply both sides by this thing. technically I didn't do it yet, but whatever. Absolute value x is going to be less than or equal to 1 plus x squared all over 2. Okay, so we've got here the image here is contained within the the interval here contains the image of the function. Interval contains the image. Now prove the image contains the interval. So for all xy, right, there exists some x in the reals such that f of x is equal to y. we let y belong to that interval, negative a half to a half, does that ruin everything? Alright, so if f of x is equal to y, and we go back and say, okay, look, this is just the original function here, then y is equal to x over equal to x over 1 plus x squared. So on one interval of x, does the function remain on negative a half to a half? Come on. Where'd you go? Come on. What the hell? That's not nice. I may have to refresh the page. I don't remember how I fixed this last time. I can't actually see my cursor. Killer King, good evening. How's it going? Yeah, there we go. Maybe. Nope. Disappeared again. Oh well. So, if y equals x over 1 plus x squared, going back to the D'Angelo book, Mathematical Thinking, worked on G5 out of the Mathematic Educator, and I think we have a reasonable solution for one of the things. Hang on, let me go back. It might work now. Alright, so the proposed problem is that k plus 1 raised to the k plus 1 is going to be greater than k to the k times 2 plus natural log of k. And that says for any real number that is for any real number such that k is greater than 1 over e. So unless I'm very much mistaken, which, you know, possible, I created a little ratio over here, knocked out one of the k plus 1s so that we had something that had an equal exponent, pulled them together, and found out that this thing is just equal to e. I mean, if you set the limit going to infinity. Now, we can't use that actually, because it turns out that it's actually greater than the original thing that we had. So, if it was between the two, that'd be really great. So we can bound it, but we can't show that it's between them. I did, however, find something that was definitely between the two. That was y equals 1. So then I said, based on that, we can show that 1 plus 1 over k raised to the k is going to be greater than 1, because this is the compound interest formula. So as long as you compound at all, right, for any k value, it doesn't matter what it is, then that's going to be greater than the 1 principal amount you started with. Doesn't matter at all what it is. Then we can show that 2 plus natural log of k over k plus 1 is less than or equal to 1 by moving stuff around, first of all. When we get down to this particular point, right, we raise up the k minus 1 from the 2 moving over as the exponent to this e, turn it into e to the k minus 1 is greater than or equal to k. And then I said, well, we can't solve this analytically, but we can figure out when this straight line is going to be intersected by this particular function. Now, you can't do it directly. You have to do it sort of indirectly by saying, if you take the derivative of each of these things, we can figure out when their slopes are equal to the same value. In this case, obviously, the linear function has a slope of 1. And then we want to know when the exponential also has a slope of 1. If it's further to the left, then they don't intersect. If it's further to the right, then they do intersect. So here we can find out that take the derivative of e to the k minus 1, it's e to the k minus 1. And then this is set equal to derivative of k is just 1. So at k equals 1, we end up with a slope of 1. So then when you plug that in, e to the 1 minus 1 is just e to the 0, which is equal to 1. So these things are tangent at that particular point, 1 comma 1. It's slightly obvious, but at the same time, it's just kind of like we have to show it. This will mean that for all real numbers, e to the k minus 1 will be greater than or equal to k. Which then, we can say down here, the natural log of these things will be in the same relationship, provided that k is such that the domain exists. So the domain of these particular functions make it such that k needs to be greater than 0. That's now the only restriction we have on this. Right? Any real number greater than 0. So then we could say, let's just backtrack everything And if we backtrack through all of it, eventually we get back to 1 plus to the k is greater than 2 plus natural log of k over k plus 1, as long as k is greater than 0. That's it. So I think we have a manageable solution for this. I don't know what is going on with the headset. Grr. Just keeps cutting out on me. Anyway, so if we go back to mathematical thinking, the hell, man, come on. Alright, you too, slowboard. Solutions to any of these problems are due in by January 25th, 2023. So we figured out 2 of them already, not bad. Algebraic manipulation, my calculus book, yep. Nice. Good job. Alright. A lot of paper and some time, yep. Yeah, and you certainly aren't the only one. We've been noticing with a lot of our calculus students a marked drop in algebraic skills, as well as unwillingness to just try stuff. See what happens? I mean, clearly you did it. So you went out there and you tried it and it worked eventually. And it's the mark of doing a good job. Do. Was it part of your homework, or was it like proof at the beginning of the section? Duo on the guy. How's it going? Welcome. I am Obi-Wan Pez. This is N Simplex Pachinko. Come on. Don't mind me. This is just... Alright, anyway. So if we have y equals x over 1 plus x squared, we want to be able to solve for x and show that the image that we're going to get from it, right, we're kind of going backwards here, so this is going to be... Come on. Really? There we go. Alright, so 1 plus x squared times y is equal to x. Yeah. Alright, so in terms of this, this is now going to be a quadratic form. So we've got y x squared. Jeez. Come on. Minus x plus. I don't know what this issue with this thing is. I mean, it's a web app, so it might just be it by itself. Tested out of college algebra when you definitely shouldn't have. Bar must have been incredibly low. Ugh. Yeah, yeah. All right, so this is a quadratic in x, and now x is going to be comma. Jeez. Equal to. All right, seriously. I'm about to reset this page. X is going to be equal to negative b, so this is going to be negative 1. So this is Mathematical Thinking by D'Angelo and West, or D'Angelo and West. Yeah, two people. All right, 1 second here. Let me. All right. So negative 1 plus or minus. I figured it out now. Okay. This is stupid, but square root. B squared is going to be our negative 1 that we have here. Negative 1 squared minus 4. A times C. A and C are both y, so this is going to end up being y squared. Over. It was not like this 2 minutes ago, I swear. 2 times A, which is y. Alright, so x is equal to 1 plus or minus square root 1 minus 4 squared 1 divided by 2y. All right. Okay. Y has a maximum value of 1/2. When you square it, it has a maximum value of 1/4. Times 4 is going to get us a maximum value of 1. So 4 y squared is less than or equal to 1. And naturally on the other side this is going to be greater than or equal to 0. But we don't really care so much about that. We know it's just going to be that. So this will have a value between 1 and 0, the square root. The square root of 1 minus 4y squared. It's going to be between, again, 0 and 1. The denominator will also have a maximum value of 1. Yes. Okay. So now 2y will be between, well, okay. Right, can't be 0. So it's going to be between, really, -1, 0 exclusive, union with 0 exclusive to 1 inclusive. And 4 I don't need the 4 there. So just note, I guess. F of 0 is going to be 0 itself. And that is our overall y value. So when x is 0, y is also 0. So that gets around this thing. We don't need to highlight it because it's all good eventually. Okay, so the numerator is going to be between 0 and 1 as well. Nope. If the square root is between 0 and 1, we have a plus, which is going to get us, okay, single value. Right, no, never mind. It's going to get us a single value that is somewhere between 0 if we have 1 for the square root and also its minus. All the way up to if it's minus and the square root is 0, it gets us 1. Then if it's plus and the square root is 0, we get 1. And if it's plus and the square root is 1, then we get 2. So we could, in theory, get any sort of value for x. Now, for the numerator, there we go. 1 plus or minus. Come on. Square root 1 minus 4y squared to be anywhere between 0 and 2. The square root is not going to be 0. No, square root can be 0. Right, that's if y is equal to a half or a negative a half. Yeah, that's okay. Just working fine earlier. Okay, and then we're divided by something that's between -1 and 0 or 0 and 1. So this could be literally any value off to infinity. And then if we were dividing by 1 and -1, this could get us, right, anything. So it's looking like this could be, all real numbers. That can't be right. Oh yeah. Yep. Okay. Oi. Come on. I wasn't having this kind of trouble before. I don't know if I've done anything. Alright, so that's going to tell us that the the image is going to contain the interval that we had. And since the interval contains the image and the image contains the interval, now we've proven that they're the same thing. So the image and the interval are the same. Goodness. Could just be the entire waveboard program. I don't know. Let's see how long it takes to load. Could also just be because there's a lot of stuff here. Which is perfectly possible. So, Duhan, we've done several other of these math books I've gone into and tried to delve. Unfortunately, my analysis skills are not really up to snuff due to the fact that I never took math analysis. Uh, because I was in a math education major, it was mostly focused on the education classes once I got up to, like, sophomore, well, junior level in undergrad. And then once I took then once I started doing my master's program, they still didn't have me take analysis. I was just basically doing whatever the teacher was doing in the classroom. Alright, subset A is a subset of reals. Now, I'm just copying the wrong letters, it's fine. S is a subset of the reals, hence S. There exists some M inside the reals, such that absolute value of X is less than or equal to M. It's like it doesn't even want me to make straight lines. It's so stupid. For all X in said subset. So some maximum distance away from 0, or maximum magnitude. Sets unbounded when no such M exists. Hey Archer. Doing quite well, thank you. How are you? Good to see you coming over from Sabrina stream. Recognize you this time. Ayo. And bounded function. Yep, we're working on some analysis because my analysis is not super great, so whoa. And Whiteboard is having a hell of a time trying to keep up with my writing and stuff like that. I have been using the Microsoft Whiteboard app. However, the problem is that when I use the actual app that's downloaded onto my computer, it crashes the stream after like, well, I mean, it crashes my entire computer after about 30 minutes or so. So then I reset the computer, log back onto the stream, and like 5 minutes later it crashes again. I'm like, alright, that's it. So I ended up taking the Whiteboard app that's online and just saying, let's use this, because it has all of my boards on it and everything like that. And, you know, well, I'm not going to exit out and show you, but, you know, I have, like, a whole list of them. Yep, so we're doing stuff out of Mathematical Thinking by D'Angelo and West. Right now it's basically just wading through definitions and stuff like that in order to get to some cool examples at the end of the section. So we'll see how it goes. Yeah, I had done like abstract algebra, and this goes to Duhon as well. Yeah, I had been doing Grinfeld, Introduction to Tensor Calculus, and also the what book is that? That's not Cliff's Notes. What's it called? Yeah, Shom's. Have been doing Shom's guide on partial differential equations, and I just kept running into roadblocks, and eventually it's really because my analysis is, well, non-existent. It's not even weak, it's just non-existent. I could also do matrix theory because, quite frankly, I should have gotten an A or B in that class, and I ended up getting a C. I was just being an idiot, spending most of my time on the other classes that I did understand. Alright, bounded functions, real valued function whose image is bounded. There we go. Well, thank you for stopping in, Archer, and we'll see you again later, I'm sure. So for anybody, Wednesday nights are math nights. I've been trying to add another one, maybe, stream like on Monday or something like that. Could just be random at this point, just to do some more math on off days, maybe at like, you know, morning time. Let's do something like that. And I was gonna plan on doing Monday math mornings, but you know. Yep, no problem. Thanks for stopping in. See you later. Yeah, and our Friday nights have been gaming nights. Lately we've been doing Valheim, and just got past no, I'm on this stream, so where's my stream? My stream is almost to Elder, so figured out where he is. We just gotta actually have enough strength to get over there and blow the thing up and not get killed in the process, or stomped, because that is very real. I remember my offline playthrough. Elder just kept stomping me. It was terrible. Realistically, I need to build a couple of teleporters in the area, but I don't have the fine wood for it. Anyway. and the image is bounded such that absolute value of f of x is going to be less than or equal to that m value that we had for all x. This is all, it just looks like shorthand, so yeah, we could just call me a master of shorthand and move on. All right. Oi. Okay. So a function will be increasing when f of x1 is less than f of x2 for x1 being less than x2. And non-decreasing when f of x1 less than or equal to f of x2. And this is really for all. It's going to be on some interval. All right. I think I'm going to refill my water, play an ad for a minute so that nobody gets any pre-rolls for like 20 minutes or something like that. So I'll be back very shortly. And thank you for sticking around, everybody. Let me know if you have any questions. Pop them in chat. Be right back. we're back. Okay. So... Alright, so then we're going to have decreasing and non-increasing, but then the signs flip to greater than and greater than or equal to respectively for those two definitions. Right, so this allows us to figure out so that's going to be monotone when non-increasing or non-decreasing on the interval. So same deal from x1 to x2. Whatever values those might be. Okay, identity function for reals mapped onto reals is going to be f defined as function that maps reals onto reals. So the identity function is going to be defined as when f of x is equal to the thing you just plugged in, x, for all x in the reals. Well, okay. Just s, so it doesn't actually matter. Right, we can generalize it. Similarly, there's such a thing as a fixed point. So ref defined as S mapping onto S. F of x equals x. For some x belonging to S, but not for all. So just right, so like sine of x plus x. For example, anytime the sine of x is equal to 0, you end up getting just x back. Alright. So this creates actually a pretty good stopping point for us. It's pretty close to 2 hours. At the very least, just stop this one. Again, if somebody's got a better idea, I would be glad to talk about it. Or else, like, talk about educational theory. Talk about why somebody wants to teach something a certain way, or maybe you name a topic and I'll think of a better way to teach it than your teacher. Right. That's putting a pretty big expectation on it. Oh. Smooth. I don't actually remember that. What is this? It's been since the beginning of April, so 2 months ago is practically forever. Oh, yeah. I was doing puzzle. have even the... See, this is the problem with me and puzzles. My spouse too, same deal. We can figure out almost any puzzle. The problem is, once you've got like all of the stuff done, extracting an answer is almost impossible for either of us. Right, according to your roomie, each of these images displays art, so A, R, and T are in the middle of the words somewhere, in order. Anyway. Hey there. How's it going? This is the problem with trying to do this sort of one-dimensionally. guys are twos. Nuts. Yeah. Trying to do this in 3 dimensions is hard enough. I gotta figure out how to. So when you start looking at n equals 4, this gets rather interesting because stage 1 is just going to be a single like this. Stage 2 is going to be tetrahedron. Can't even draw it properly. This point is just making too much of a mess. Well, anyway, now that you've sat through that. In 4 dimensions, an interesting thing happens with our 4 simplex, and that is that each of its layers are one of the previous 3 simplices from below. So every time we add a row and go down, it's going to start looking more and more and more complicated, just like each individual row of this one here. It's also true if we trace all the way back, right? N equals 1 is just an unbroken line of 1s. N equals 2 has those 1s as edges. N equals 3 has those Pascal triangles here as faces to a new tetrahedron. I'm not doing it justice with n equals 3 here. I thought that by like drawing a graph it might make it a little bit easier, but yeah, it's just gonna be all sorts of messed up. And then with n equals 4, each of the states that we got in n equals 3 end up becoming, one side of the n equals 4 simplex, or 4 simplex. Would at some point like to fix that and do like a, make a program or something that would jump around a little bit and figure out some cool stuff, but yeah. All right. So I think tonight it is time to hop on over to Boss Lady. Go see her, and hope you all have a good week. I'll see you on Friday for games and Wednesday for more math stuff. Till then, good luck, stay safe, and this is Obi-Wan Pez for and Simplex Pachinko, signing out.